What exactly is the heap? What does malloc really do? Those are questions we try to answer in this video. You may have learned that when you are programming and you need some more memory, you use the heap by allocating memory with malloc, and later you free it again if you don't need it anymore. And somehow some magic is happening and you don't really know how, but you magically get more memory. Before we talk about malloc, let's first talk about how our process gets any memory in the first place. This is done via mmap or brk. Those are system calls, which means we ask the kernel directly. Mmaps asks the kernel to give us some new virtual address space, basically requesting a new memory segment. Besides mmap, there's also brk, which can be used to change the size of an already used memory segment. This is all real fucking magic. In the end, the process doesn't care how this memory is implemented, if there's RAM, where exactly on the RAM you store it, or if you have a swap file because you don't have enough RAM. The kernel and hardware take care of this and maps the memory into the process. This means that the process can transparently access those memory addresses and work with them. And transparent in this context means doesn't have to know anything about it. You can execute heap1 with strace, and you see all those calls to mmap to initially set up the process memory regions, and near the end it uses brk to set up the heap. So why don't we just use mmap or brk to get more memory for our process? And why do we always talk about the heap with malloc and free? Well, malloc is just a very fancy and convenient wrapper that handles the brk or mmapping for us, and does much more. Malloc will call mmap or brk to get more memory if the heap doesn't exist or is too small, but on top of that it will also help us to organize and manage that memory. Also during CTF challenges, and the example we will have a look at shortly, use the heap so little that we don't see any additional memory mapped regions. So to keep things simple, we consider the heap to be just a big chunk of fixed memory mapped memory. And we can do in this memory whatever we want. So when we refer to the heap, we actually mean this memory region. So what does it mean that malloc will manage the heap? Let's explore this abstractly first. We want to allocate 8 bytes. So we call malloc with 8. This means we block 8 bytes on the heap. Each call to malloc will return the address of the heap where the area got blocked. And with this address we know we can write our 8 bytes to. So we can now write the string A, B, 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 B to that address. And now let's allocate 2 more times just to see what would happen. Malloc 8 and malloc 8. This begs the question, how does malloc know which areas are still free? So there are many different ways one could implement that. Though most commonly used is an implementation called dlmalloc, because a dude with the name Douglas Lear wrote it. And that malloc algorithm will store for each chunk a block size of the chunk right before it. And it will also keep 4 bytes before that empty for how the free is implemented, but we will only focus on malloc for now. Let's do the mallocs again and let's think like a computer. So at the start, when the first malloc is called, we obviously know the beginning of the heap. So we store the size that we want to allocate there and return the address where the chunk part that is usable by the programmer starts. But how does malloc know on the next call to malloc where the next chunk can be placed? Not that we overwrite our previously allocated area. Well, we obviously have to kind of memorize where our free region begins. So malloc will simply do some math and update the address that pointed to the beginning of the heap by adding the size of the chunk we allocated to it. And this happens with every malloc. So there's a pointer somewhere that will always point to the free memory. Cool. And just for understanding purposes, given the return address of malloc, what can you do with that? Well, this pointer points to the start where we can write data to. So if we look at the address just before that, we can read the size of the current chunk. And if we know the size, we can add that size to the address to get the next chunk on the heap, where we can do the same again. Now, let's have a look at the heap level 1 challenge from Protostar. We will use that example to look at how malloc works in real life. But first, let's step through the code line by line and try to imagine how the heap will look like. And then next video we will actually do that practically. The objective here seems to call winner, so we somehow have to redirect code execution to that function. At the top there is a struct defined called internet, which has two members, a priority integer and the second member is a char pointer called name, which means names contains a pointer to a string somewhere else. Structs are like classes, at least in terms of providing a structure with multiple different member attributes. Now, main defines three variables from the type struct internet pointer, but only two are used. I guess a leftover from creating this level. I emphasize struct internet pointer because those three internet objects are not stored on the stack. Only the addresses, the pointer to those objects, are stored in I1, I2, and I3. Anyhow, then it starts allocating those objects on the heap. It first calls malloc with enough space for the object I1. Size of will return the number of bytes the structure requires. In this case that's 8 because the integer priority is 4 bytes and the char pointer, which is an address, is also 4 bytes because we are on a 32-bit machine. And we know that malloc returns the address on the heap that we can now use. So I1 points to the start of 8 bytes in memory. And now we want to set priority to 1, which will write 1 to the first 4 bytes of the allocated area. Then it allocates another 8 bytes, and the resulting address will be stored in the char pointer name, which is at offset +4 of the I1 object. As a programmer, we write I1 and arrow name to access the name attribute, but implemented is it as simple going to a certain offset of I1. In this case, I1 +4 is the location of the char pointer name. So now I1 arrow name will contain an address which points to the allocated heap area which we just allocated. Those 8 bytes are intended to store a list of characters, a string, the name. Then the same is done over again for I2. We make space for the struct I2, we set its priority to 2, we allocate another 8 byte for the name string. So we basically have now 2 objects allocated on the heap that we can work with. Next come 2 str copies. And we know that string copy is always super suspicious because there's no length indication and we can potentially write more than we have space. In this case, the internet name was allocated with only 8 bytes, so we could probably write over those 8 bytes and really screw up stuff. Anyhow, the string copy will copy the first argument to the name of the I1 object. I1 points to the start of the I1 object, and at offset +4, which is the name, is the address of the free 8 bytes that were allocated for the string. So string copy will take the address stored there and copy the string from argument 1 at that location. And the same thing is happening for the second argument with the I2 object. After that we will printf and then quit the program. In the next video we will have a look at the heap while we execute this program to understand how the heap looks in real life and how we can work with it in GDB and in the end solve this challenge. Oh, by the way, I lied. I said the second word would contain the size of the chunk. Well, it does, but also the lowest bit is used to indicate that the previous chunk is used, not free. That becomes more important for the free algorithm. Thus in our example, those values would all be hex 11. I just want to put a small disclaimer here at the end. I simplified the heap and malloc a lot. For example, I only talked about one pointer pointing at the free area. In reality, there's obviously way more to this. And if we look into the history of exploitation, we are currently looking at stuff from more than 15 years ago, like 2001-ish. A lot of the stuff hasn't changed and the concepts are the same, but a lot of stuff is also different. Today's malloc implementation is based on dlmalloc, but it's not really the original dlmalloc anymore. Now it's usually referred to as ptmalloc. And my goal here is to teach you the fundamentals. Even though it's not 100% correct, you should have now a rough idea what the heap is and what to look for, and you can transfer this knowledge to any heap implementation.